Well testing. This online course covers the general well testing theory of operations and calculations knowledge. By the end of this course, you will be able to calculate gas-oil ratio, GOR, and productivity index, PI, to evaluate well productivity, and you will have a good knowledge of the different types of well tests, well testing equipment, well testing safety measures, well testing sequences, and well testing data. This well testing course covers the following topics. Chapter 1. Well testing introduction. Chapter 2. Drill stem testing overview. Chapter 3. Tubing conveyed perforation overview. Chapter 4. Surface well testing overview. Chapter 5. Well testing layout. Chapter 6. Well testing safety. Chapter 7. Types of well tests. Chapter 8. Well testing sequences. Chapter 9. The cleanup period. Chapter 10. The well test data. Chapter 11. Productivity. Chapter 1. Well testing introduction. Well testing history. Fossil fuels have been used by man for generations. The Industrial Revolution created a large demand for fuel to supply the emerging industries and the corresponding social changes. Initially, oil was mainly obtained through whaling and other animal fats. However, the availability of surface oil deposits was creating specific excitement among the scientific community. The first commercial oil well was drilled near Oil Creek, Pennsylvania, by Colonel Edwin L. Drake in 1859, which marked the birth of the modern petroleum industry. Well testing techniques were first applied in the early 1920s. A simple pressure measurement was taken using a Borden tube and stylus arrangement. Early analysis techniques were presented by Muscat in the 1930s and later in the 1950s with the classical work of Miller, Dyes, Hutchinson and Horner. Electronic recording devices in the early 1970s and computerized systems in the early 1980s set new standards of data acquisition and interpretation techniques. Well testing overview. When drilling a well, the client has a number of questions to answer. What is the size of my reservoir? How much will it produce? What fluids are going to be produced? The aim of well testing is to answer these questions by the identification of produced fluids, the determination of reservoir deliverability, and, later on, the well test data collected will be used to predict the reservoir size. Well testing determines production capabilities and reservoir properties. Well testing is the only technique that examines a significant portion of the reservoir under dynamic conditions. Accurate, long-term projections about a reservoir cannot be made based on wireline and other static techniques. Tests on oil or gas wells are performed at various stages of drilling, after open-hole logging, completion and production, and for different purposes. The data acquired when a reservoir is tested includes the flow rates of oil, gas, water, and solids produced, the pressure and temperature recorded at surface and at bottom hole, the PVT samples of representative reservoir fluids collected at surface and at bottom hole. What is well testing? Well testing is the only technique examining a significant portion of the reservoir under dynamic conditions to determine its production capabilities and reservoir properties. Tests on oil or gas wells are performed for different purposes at various stages of drilling, completion, or production. It is important to fully understand the reason for each of these tests and what is expected to be accomplished with the results. It generally consists of identifying, measuring, and sampling, and finally disposing of the well effluent produced during these operations that involve flowing the test zones from just a few hours to a few days. The flowing period normally precedes the shut-in of the well. Pressure buildup data analysis provides invaluable information about the producibility of the well and the extent of the reservoir that is being drained. Aim of well testing. The aim of the well testing is the identification of the produced fluids and the determination of the reservoir deliverability. Well test results may have far-reaching effects on future field development planning. Therefore, it is most important that objectives are clearly defined and the well test programs are designed accordingly. Most well tests can be classified as productivity tests, which is a simple identification of produced fluids and determination of reservoir deliverability. Or descriptive reservoir tests, which consist of definition of complex reservoir features. Sequences of well testing. In order to produce oil at surface, the first step consists of perforating the reservoir using tubing conveyed perforations, TCP. The next step consists of using the DST drill stem test equipment to convey the flow to surface. The main DST equipment includes the packer, the tester valve, the tubing or drill pipes and, eventually, the subsurface safety valve. Finally, the surface well testing equipment are used to handle the flow at surface. It includes the flow head, the choke manifold, the burners, and others more. This picture shows the complete setup of a well testing package from bottom hole to surface. Well testing measurements. The required measurements from well testing are the rates of each fluids produced, the bottom hole conditions behavior, and the PVT study of representative reservoir samples. The purpose of a DST or production test. 1. Determine the nature of fluids produced. PVT analysis are performed at bottom hole conditions or from surface recombined samples. 2. Define the well productivity. Productivity index and IPR plot for oil wells, or deliverability curve and absolute open flow, AOF, for gas wells. 3. Evaluate the characteristics of the producing formation. Determine static pressure, PI, and formation flow capacity, KH, for reservoir heterogeneity and limits. 4. Evaluate any formation damage, skin factor, S. Determine if acidizing or other treatment is required and control the results of the stimulation or treatment. Chapter 2. DST Overview. What is DST? DST, drill stem testing, is a temporary completions with different combinations of downhole tools run on drill pipe or tubing. DST is used equally to control the well during dynamic test operations. DST concept. DST, drill stem testing. The primary DST functions, whether conducted in open hole or cased wells, are to isolate the target zone, control well flow, convey fluid to surface, and acquire downhole data. The three basic equipment of a drill stem test, DST, consist of a string, tubing or drill pipe, a packer, and a valve. The string channels the flow to surface. The packer is a rubber element to isolate the zone to be tested. The valve provides a method of controlling the well near the reservoir. The three basic pressures involved in a DST are the hydrostatic pressure pH, the formation pressure PF, and the cushion pressure PC. Generally, the relationship among these pressure is pH greater than PF and PF greater than PC. The packer isolates the formation from the annulus. The two pressures, pH and PF, must be isolated from one another. The tester valve controls the formation, shut the well downhole to minimize wellbore storage effect, isolates annular fluid from cushion while running in hole preventing U-tubing, and provides a seal for pressure test the string. After the packer is set and sealed, the tester valve can then be opened and hydrocarbons can be produced to surface. This will occur only if PC is less than pH. The general steps for ending a DST are: 1. Open the reverse circulating valve and reverse out, flush hydrocarbons from drill pipe or tubing. 2. Close the reverse circulating valve. 3. Open the tester valve. 4. Pump mud into test string to kill the tested interval. 5. Unseat the packer. 6. Pull the string out of the hole. During the initial phase of the test, the wellbore fluids, and later, the drilling fluid, mud, that has invaded the formation in the vicinity of the wellbore, flow to surface. This is known as the cleanup period. The cleanup is complete when the well effluent at surface is reservoir fluid that contains no mud particles or cuttings at surface. Once cleanup is complete, the main flow period can be maintained for the planned duration, during which downhole pressure measurements and surface flow rates are recorded. At the end of the main flow period, the tester valve is closed. Formation pressure builds up against the valve while downhole pressure measurement continues. There are three main types of DST available. Open hole DST, where packer is set in the open hole section of the well. Barefoot DST, where packer is set in the casing section but the well is flowing from open hole. Cased hole DST, where casing needs to be perforated in order to flow the well. And very rarely straddle DST, used in open or cased hole. Different DST configurations may be used depending on well location and configuration, either for land rig, offshore fixed, offshore floating, or deviated well. DST packers. Packers are designed to isolate the perforated interval from the mud column. The weight applied on the packer compresses its rubber elements against the casing and creates a seal between the annulus and tubing. Three main types of packers are available: FlexPack packer, Positist packer, and Positreve packer. DST tester valve. Various types of tester valves are used. Multi-flow evaluator. It is operated by manipulation of the test string and it is generally used onshore and on jackup rigs. Pressure controlled tester, PCT. It is operated by annulus and tubing pressure, and it is generally used offshore and on floating facilities. Intelligent remote system. It is operated by pressure pulses in annulus and it is generally used offshore and on floating facilities. Typical DST TCP tool string. A typical DST TCP tool string is composed, from bottom to top, of perforating gun, safety spacer, firing head, tubing, debris sub, slotted tailpipe, packer, safety joint, hydraulic jar, pressure recorders, hydrostatic reference tool, downhole valve, surface readout, drill collars, radioactive marker sub, surface readout, drill collars, redundant circulating valve, drill collars, slip joints, and finally, tubing or drill pipes. Chapter 3. TCP Overview. What is TCP? TCP, tubing conveyed perforation. Perforation is the act by which communication tunnels are created from the casing or liner into the reservoir formation through which oil or gas can be produced. Tubing conveyed perforating TCP guns are used in situations where either underbalanced perforating is desired over a long interval or when the deviation is so high that wireline conveyed guns cannot be used. TCP is an efficient way of perforating long intervals because it minimizes the number of trips in the whole perforation job. The most common method uses HSD perforating guns equipped with shaped explosive charges. Why TCP? In order to produce oil at surface, we need to do perforation. After running the TCP string in front of the desired reservoir formation, the guns are fired, creating communication tunnels from casing to the reservoir formation, through which hydrocarbon can flow to surface. Explosives used for TCP. Three main types of explosives are used in the industry for TCP applications: HNSHTX, HMX, and RDX. The selection will depend on bottom hole temperature and time of exposure. General TCP safety. TCP guns will be loaded at the rig. B. Agree where the guns will be loaded. Where the explosive bunker will be placed. Have work permit done before any explosive work. Good communication is key to a successful job. JSA, job safety analysis, will be performed before each step of the DST TCP operation. For example, pick up TCP guns. Run in hole with DST TCP. Perforate the well. Killing the well. Rig down TCP guns. Chapter 4. Surface Well Testing Overview. When performing well tests, the following items must be addressed. Requirements of dynamic conditions. Type and layout of surface testing equipment. Equipment needed to collect samples at the surface. Safety requirement. Creation of a pressure disturbance depends on whether the reservoir is producing or shut in. If the well has been shut in for a long time, is to flow the reservoir, this is called drawdown. If the well has been flowing for a long time, is to shut in the well, this is called buildup. Surface testing equipment must safely and reliably perform a wide range of functions. Quickly control pressure and flow rates at the surface and shut in the well. Separate the effluent into 3 separate fluids, oil, gas and water, accurately meter the fluids, collect and separate solids as applicable. Collect surface samples. Dispose of the resulting fluids in an environmentally safe manner. This picture shows a complete well testing package. Surface well testing equipment. In order to handle the well effluent at surface, a standard set of surface well testing equipment should include the following: flow head, safety valve, sand filters, choke manifold, emergency shutdown (ESD), heat exchanger, separator, gauge or surge tank, transfer pump, oil and gas manifolds, burners and booms. The flow head controls the well pressure. The choke manifold controls the flow and the pressure. The heater, or steam exchanger, is used to raise the effluent temperature to fight hydrates in gas wells, and to break emulsion, or to reduce foam and viscosity in oil wells, and improve burning. The separator is used to separate, meter and sample the 3 phases of the effluent. The gauge or surge tank is used to store oil, to calibrate the liquid meters, to measure the shrinkage and low liquid flow rate. The transfer pump is used to empty the tank and to ensure proper atomization pressure for clean burning at the burner head. The oil is disposed of through the burner, located at the extremity of the booms, to reduce heat radiations towards the rig. The gas is burned separately through a gas flare, located on the burner booms. The various elements of the surface well testing chain are interconnected with piping, generally flexible between flowhead and choke manifold, and rigid elsewhere. Flexible piping. 1. High-pressure flexible hose, ended with Wico union or greylock connections, is used between flowhead and choke manifold. It is called co-flexip. 2. Low-pressure flexible rubber hoses, ended with Wico union connections, are generally used for air and water lines. High-pressure flexible hose, co-flexip, is used between flowhead and choke manifold, to allow up and down movement of the DST string during DST tools operations, keeping the flow line connected to the burner via the choke manifold. Long length available, 40 feet or 60 feet, which reduces the number of seals and risks of rupture or leak. Co-flexip hoses are heavy, and the use of a crane is mandatory to rig it up safely. To respect the MBR, minimum bending radius, a couple of elbows, may be used both ends of the co-flexip hose. Rigid piping. Rigid piping are generally ended with Wico union connections, or greylock for high-pressure lines. Generally, straight piping are often 1 meter, 3 meters or 5 meters long. Elbows are often 90-degree. Chapter 5. Well testing layout. Typical surface well testing layout. The well testing layout is a representation of the individual pieces of equipment put together for the purpose of producing the well at the surface. On this picture, you can identify the name and the position of the different pieces of surface equipment that compose the surface well testing setup. The layout diagram. The layout diagram defines which pieces of surface testing equipment have to be used. Identifies where the equipment is located according to zones and recommended distances. It illustrates the sequence in which the equipment is connected. And shows the general piping with vent lines layout, emergency shutdown, and air lines. The layout diagram varies according to location, land or offshore operation, and well conditions such as sand production, flow rate and pressure, presence of corrosive fluids, H2S, CO2, and acid, effluent properties, oil properties and hydrate formation. Onshore layout diagram. In an onshore layout diagram, the oil and gas pits, both must be located about 300 feet from wellhead and testing area, and also be separated from 300 feet. The oil burners used are two, both must be located about 150 feet from wellhead and testing area, and also opposites. The vertical gas flare used, generally one, and must be located about 300 feet from wellhead and testing area. Nowadays, burners are more frequently used than burning pits on land, for both safety and environmental reasons. Lines to oil and gas pits, burners, or flare, must be secured, and/or anchored to the ground to prevent whipping. Generally tubings are used for flare lines and vent lines. Crossovers are needed between tubings and well test piping. Offshore layout diagram. Some offshore rigs have permanent piping, rig's property, to facilitate the connection between the different pieces of equipment. Generally, they are available between the rig floor and the surface well testing area, and between the surface well testing area and the booms area. Permanent piping may be used if it complies with the industry pressure safety precaution. Layout general rules. Placing the choke manifold on the rig floor, it limits the length of high pressure piping. Reduces the pressure drop between flowhead and choke manifold. Gives more accurate wellhead pressure and wellhead temperature. The piping between flowhead and choke manifold is called flowline. The flowline must be flexible on all floater rigs, and it is recommended on all other fixed rigs. Offshore, two burners mounted on booms, one on each side of the rig. One burner or the other is used, depending on the wind direction. Burners require compressed air to properly burn the oil, and propane is necessary to supply the pilot lights for the burners. A water pump is used to inject water into the oil flame at the burner, old generation, and to create a water screen behind the burners, which reduces heat radiation. Whenever H2S presence is expected, gas shall be vented to flare. Correct piping size prevents very high fluid velocities, large pressure losses, overpressurization of the equipment. In some tests, the effluent may be injected into a pipeline or production line. Chapter 6. Well testing safety. Safety is a major factor in designing and conducting a well test. Piping, flow lines and all vent lines must be anchored. Piping must be color-coded to identify the working pressure of the pipe. All pieces of surface testing equipment must be grounded. Equipment layout and spacing must be in accordance with classified zones. The dominant wind direction must be identified to properly orient equipment that vents or burns gas. Electrical connections, such as transfer pumps or laboratory cabins, must be safe and approved according to industry standards. Classified zones. A well site is classified into zones, or areas, based upon the probability that flammable gases or vapors may be present around a specific piece of equipment. It is recommended not to overlap classified zones. Zone restrictions do not dictate the placement of all well test equipment. For example, the ESD system and oil and gas manifolds, usually placed in Zone 2, are not restricted to that specific zone. For further information on the zone classifications, see API 64B. Zone 0. Area where any flammable or explosive substances are continuously present. For example, the borehole, the well below the wellhead. Zone 1. Area where any flammable or explosive substances are processed, handled, or stored. For example, the gauge tank, gas release from vent in the immediate vicinity. The choke manifold, sampling causes some gas release. The flow head, due to tool's introduction during a well test. When tool's introduction are not being made, the flow head is Zone 2. Most electric-driven transfer pumps. Zone 2. Area where any flammable or explosive substances are processed and stored under controlled conditions. For example, the separator in case of a leak. The indirect fired heater, because it uses a naked flame. The steam exchanger, because it can reach high temperatures. Piping is defined as a Zone 2 area. Diesel-driven transfer pumps, if equipped with automatic shutdown system, sparks arresters, inertia, or special electric starters. Clean zone, also called non-hazardous or safe areas. Area where no flammable or explosive substances are processed, handled, or stored. For example, the living quarters of an offshore drilling rig. Onshore recommended distances. This picture shows for an onshore rig or land operations the recommended zones distances around each piece of the surface well testing equipment. It also shows the recommended distances to be considered between each of these individual pieces. Offshore recommended distances. This picture shows for an offshore rig operations the recommended zones distances around each piece of the surface well testing equipment. It also shows the recommended distances to be considered between each of these individual pieces. Equipment safety standards. The top area around the separator rupture disc pipe is classified as Zone 1, with 15 feet or 5 meter around. The area within 15 feet above the roof of the gauge tank is classified as Zone 1. H2S requirements and safety. Hydrogen sulfide, H2S, is a dangerous gas because it has a wide explosive range and is highly toxic. H2S properties. Color, none. Odor, extremely offensive, smells like rotten eggs. Density, 1.189, it is heavier than air. Explosive limits, 4.3% to 46%. Ignition temperature, 500 degree Fahrenheit, or 260 degrees Celsius. Water solubility, for volumes of H2S gas, is soluble in 1 volume of water at 32 degree Fahrenheit, or 0 degrees Celsius. H2S toxicity. At 1 ppm concentration, or 0.0001%, H2S can be smelled. If more than 1 ppm, leave the area or use PPE. At 10 ppm concentration, or 0.001%, a maximum 8 hours work period is allowed. If the H2S concentration is more than 100 ppm, or 0.01%, the odor disappears, the eyes and the throat burns, loss of consciousness, permanent brain damage or death. H2S operation guidance. Mandatory pre-job safety meeting for all personnel involved. Constant supervision of the job and use a minimum of 2 experienced, H2S certified engineers or technicians. Do not allow H2S to escape into the atmosphere in any place where it can accumulate. Monitor the wind direction constantly. Wear breathing apparatus when surface sampling, measuring gas-specific gravity, changing Daniel orifices in chokes, bleeding off pressure, and walking on burner boom. Operate instruments with compressed air. In addition to its adverse health effects, H2S is highly corrosive to metals. Equipment not positively identified as H2S service must be assumed to be not rated for H2S service. Welding performed outside a qualified shop on H2S equipment invalidates the H2S rating. Piping with threaded connections is not rated for H2S service. Use only a surge tank offshore. Never use an atmospheric gauge tank offshore. Heat radiation. Problems associated with heat radiation arise primarily during burning operations and are a serious problem for both personnel and equipment. 330 British thermal unit per hour per square feet, is the greatest solar radiated heat at soil level. 440 British thermal unit per hour per square feet, is the upper limit for harmless exposure of bare human skin. 1500 British thermal unit per hour per square feet, is the API, RP521, recommended upper limit for an oilfield worker, wearing work clothes, and intermittently sheltered, or sprayed with water. Easy solutions, for managing excess heat, are to inject water into the flame. Use longer booms, 85 feet or 26 meter. Install additional water screens behind the burners. Install water ramps, alongside the hull, where excess heat can be radiated. Noise pollution. Ear protection is critical for all personnel exposed to noise during well test operations. According to the ISO noise exposure recommendations, at 90 decibel noise level, the permissible exposure is 8 hours per day. At 95 decibel noise level, the permissible exposure is 4 hours per day. At 100 decibel noise level, the permissible exposure is 2 hours per day. At 105 decibel noise level, the permissible exposure is 1 hour per day. At 110 decibel noise level, the permissible exposure is half an hour per day. At 115 decibel noise level, the permissible exposure is 10 minutes per day. For example, a separator, flowing 4,000 barrels oil per day, with a GOR of 300, generates a noise level of 62 decibel. From 100 feet, a 6-inch gas line, with 10 million standard cubic feet per day, generates a noise level of 96 decibel, and with 35 million standard cubic feet per day, the noise level is 107 decibel. Electrical safety. Electrical equipment located in hazardous areas must meet protection standards. The most commonly used means of protection are intrinsic safety. This is a protection technique for safe operation of electrical equipment in hazardous areas by limiting the energy, electrical and thermal, available for ignition. Explosion proof. Meaning that the enclosure of the electrical equipment, classified as explosion proof, must be able to internally withstand any internal explosion, any sparks generated internally, and preventing these sparks from igniting any vapors, gases, fibers, or dust in the surrounding environment. Chapter 7. Types of well tests. Well testing review. Well testing is the only technique that examines a significant portion of the reservoir under dynamic conditions to determine its production capabilities and reservoir properties. DST concept. DST, drill stem test, is a temporary completion with different combinations of downhole tools run on drill pipe or tubing. It is used to control the well during dynamic test operations. Its primary functions, whether conducted in open hole or cased hole, are to isolate the target zone, control well flow, convey fluid to surface, and acquire downhole data. Types of well tests. During the drilling phase of the well, a drill stem test, DST, is normally performed. Different types of DST are performed at various stages of drilling. Either open hole DST or cased hole DST. During the exploration phase of the well, a drill stem test, DST, is normally performed to test the well. During the development phase of the well, drill stem test or production test can be done to test the well, depending on the well test objectives. When performing a drill stem test, DST, we use retrievable packer, tubing or drill pipe, and flowhead. On the other side, when performing a production test, the permanent completion packer will be used, as well as tubing and the Christmas tree. Exploration tests. Open hole DST. Normally short test, less than 12 hours, using flowhead. During drilling, unexpected traces of hydrocarbons appear. Run in hole and open hole DST to determine whether a true reservoir exists. This type of test is now replaced by wireline tools such as RFT and MDT. Cased hole DST. If logs and open hole DST results are promising, casing will be run in hole, then perforations are done. Flowhead is used. The test duration is normally a few days, 3 to 10, during which oil and gas are burnt. Most of the time they are plugged and abandoned. Production tests. Production or completion tests, they are done sometimes with a rig still present. The test duration is longer than DST. Flow rates can be more realistic, and a gain in reservoir information is obtained. Christmas tree, permanent completion and packer, SSD, and nipples are used. Reservoir limit tests. This is a long-term well test, from 1 to 4 weeks, to determine the extent of the reservoir. Extended well tests. This is a long-term well test, a few weeks to a few months. During this type of tests, the operation uses part of EPF or EPS setup. It enables comprehensive evaluation of complex reservoirs before possible future development. EPF, Early Production Facilities. EPS, Early Production Services. These type of production tests are a very long duration tests. Generally, a few months to a few years duration. During these tests, the crude oil, or gas if gas field, are exported. They provide early cash flow, while permanent facility is under construction. They are a temporary replacement of existing production installation in case of shutdown for upgrade, etc. They are an alternative for marginal fields. Interference or pulse tests. This type of well tests is performed to establish communication between two or more wells, and to determine inter-well reservoir parameters. Generally one well is shut in, the observer, with bottom hole gauges, and another well is flowing, with the surface well testing setup. Chapter 8. Well testing sequences. The first two operations of any well test sequence are pressure testing the equipment and cleaning up the well. The last operations in the well test sequence involve flowing the well at one rate or several successive rates, taking representative fluid samples, and recording the pressure buildup during a final shut-in. Basic sequence of operations. An initial well test program depends on the reservoir and the well characteristics. It is established after a detailed analysis of all the information available from geophysics, drilling, logging, etc. The recommendations given here are a summary of the industry experience over thousands of tests. Sequence of operations, exploration test. 1. Pressure test of the surface equipment. 2. Initial flow, communication from reservoir to casing. 3. Initial shut-in to measure or estimate initial reservoir pressure, PI. 4. Clean up, till clean. 5. First shut-in, optional. 6. Flowing at one or several successive flow rates. 7. Taking representative fluid samples. 8. Final shut-in, to record pressure buildup, duration according to reservoir permeability. On this pressure graph from downhole gauge recorders, we can identify the following well testing sequences. Taking note of hydrostatic pressure pH. Open the well for an initial flow of 5 minutes, to establish communication from reservoir to casing. Close the well for an initial shut-in period, for 1 hour, to estimate initial reservoir pressure PI. Open the well for a cleanup period on adjustable choke, gradually increased to 64/64. Determination of the best choke size, for optimum flow without depletion. Closed the well for a first shut-in period. It is optional to run in whole downhole gauges or surface readout. Open the well for a first flowing period on 32/64 fixed choke. Increase the choke size for a second flowing period on 64/64 fixed choke. This is called the main flowing period or drawdown through the test separator on several fixed choke sizes. Taking sets of representative surface samples at the end of the main flowing period. Close the well for a final shut-in period to record pressure build-up. Open the well for flow on 16/64 to take representative bottom hole reservoir samples. Killed the well. Pull out of hole DST tools. Downhole pressure gauge recorders at surface. Sequence of operations, production test. 1. Clean up, till clean. 2. First shut-in, optional. 3. Flowing at one or several successive flow rates. 4. Final shut-in to record pressure buildup, duration according to reservoir permeability. On this pressure graph, from downhole gauge recorders, we can identify the following well testing sequences. Open the well for a cleanup period on adjustable choke, gradually increased to 64/64. Determination of the best choke size, for optimum flow without depletion. Closed the well for a first shut-in period. It is optional to run in whole downhole gauges or surface readout. Open the well through the test separator for a main flowing period on fixed choke. This is called the main drawdown. Taking sets of representative surface fluid samples at the end of the main flow period. Close the well for a final shut-in period to record pressure build-up. Pull out of whole downhole tools with pressure gauge recorders. Downhole pressure gauge recorders at surface. Chapter 9. The cleanup period. Why cleanup period? The purpose of the cleanup period is to eliminate all foreign fluid, mud filtrates, completion fluid, etc., contained in the invaded zone and the wellbore, so that representative reservoir fluids may be produced during the well test. To establish the highest possible flow rate compatible with the well equipment, reservoir characteristics, and surface equipment capabilities. To avoid sand breakthrough, and to use a choke, at least, as large as the largest choke that will be used during the actual test. Limits of the cleanup. The 3 limits of the cleanup period. 1. Flow rate and pressure should be the highest compatible with surface well testing equipment to monitor carefully the pressure, downstream choke manifold, limited by the working pressure of piping, separator manifold inlet, burners, etc. 2. In gas well, the drawdown should not exceed 25% of the static pressure. For example, if the wellhead shut-in pressure equals 5,000 psi, the wellhead flowing pressure, still upstream choke, should not go below 3,750 psi. 3. In gas well, gas velocity should not exceed 160 feet per second in case of dry gas well, and 80 feet per second in case of gas well with liquid and solids. Note: these values are recommended to be respected between choke manifold and separator, principally downstream chokes, at choke manifold and heater. The gas velocity may be obtained using the gas velocity chart. Line sizing and securing recommendations. Offshore and onshore, we recommend the use of clamps with slings or chain around unions. Slings or chains to be further attached to fixed points. Supports and clamps should be welded to deck on offshore rigs. Heavy concrete load should be used on land rigs. These safety recommendations should be applied for all flow lines and must be used for all high-pressure piping and vent lines. Critical flow. The critical flow is a flow condition that occurs across the choke, in which pressure fluctuations downstream of the choke cannot affect the conditions upstream of the choke. The choke is called effective when critical flow is achieved through it. It is good to flow under critical flow conditions, because any variations of pressure downstream the choke, at heater, separator, oil manifold, tank, etc., will not affect the pressure and flow rate upstream the choke and on downhole gauges recorder. Critical flow occurs when the flow velocity in a channel equals the wave velocity generated by a disturbance or obstruction. In case of a critical flow condition, the fluid can only move downstream. The amount of fluid coming down is so great that no fluid can flow upstream. In case of a non-critical flow condition, the flow can move in both directions, which will badly affect the pressure and flow rate upstream the choke and the data recorded on the downhole gauges. Critical flow conditions through a choke exists when 1. For an oil well, the downstream pressure is less than 0.6 times the upstream pressure. 2. For a gas well, the downstream pressure is less than 0.5 times the upstream pressure. Gas-oil ratio. The gas-oil ratio, in standard cubic feet per barrel, or cubic meter by cubic meter, is equal to the gas flow rate, in standard cubic feet per day, divided by the oil flow rate, in barrels per day. If the GO are greater than 5,000 standard cubic feet per barrel, this is a gas well. If the GO are less than 5,000 standard cubic feet per barrel, this is an oil well. For example, if a GOR equals 4,000 standard cubic feet per barrel, that means this is an oil well, and for each barrel of oil produced, the well is producing 4,000 standard cubic feet of gas. In case of an oil well, if the GOR is unknown, it could be estimated using a rule of thumb. GOR, in standard cubic feet per barrel, is equal to 0.1 times the depth of the flowing reservoir in feet. Cleanup duration. The estimation of the duration of the cleanup period, or well is it producing clean hydrocarbons to consider the cleanup is achieved, depends on several criteria. 1. BSW less than 1% solids. The basic sediment and water is frequently taken at the choke manifold. If you pass flow through separator with more than 1% solids, it will be full of solids rapidly, etc. 2. Salinity measurement of water, if any. To confirm if water is coming from formation, or is it mud or cushion. If the water is not coming from the formation, the BSW must be less than 1% to consider cleanup finished. If it is formation water, the well is producing water and there is no limit in BSW percentage, to consider that the cleanup is achieved. 3. pH measurement, after acid job. Check if pH greater or equals 7. Measurements done on produced water collected from BSW tubes. Acid will damage mechanical devices from separator, piping, tanks, etc. 4. Stabilization of wellhead pressure, particularly for gas wells to determine if the wellbore is free of liquids. Frequently check wellhead pressure is steady with dead weight tester, Foxborough, and on real-time data acquisition system if available. 5. Stabilization of bottom hole pressure, whenever surface readout system is available, which is rarely used during cleanup. 6. Visual examination of the flare. White or gray smoke may indicates presence of water. Fast changes may indicates venue of water surges. 7. A minimum amount of fluid has been produced, at least equal to the wellbore volume, tubing content plus rat hole content. 8. Surface flow rate stabilization, using choke performance charts. Chapter 10. The well test data. The data collected during well testing operation are the day-to-day results provided to the petroleum engineer in a daily well testing report. These data includes 1. Rough gas composition, H2S and CO2. Taken using Draeger pump with reactive tubes. 2. BSW, basic sediment and water. Taken using hand or electric centrifuge machine. 3. Wellhead pressure. Taken using dead weight tester, Foxborough chart recorder, mechanical dial pressure gauge, or electronic pressure sensor. 4. Wellhead temperature. Taken using alcohol thermometer, Foxborough temperature recorder, or electronic temperature sensor. 5. Specific gravity for oil. Measured using hydrometer and thermometer on an oil sample from the oil outlet separator. 6. Specific gravity for gas. Measured with Ronarex gravitometer. 7. Oil flow rate. Measured with the 2-inch or 3-inch oil flow meter located on the oil outlet of the separator. 8. Gas flow rate. Measured with the Barton chart recorder and the Daniel orifice meter. 9. Water flow rate. measured with the 2-inch water flow meter located at the water outlet of the separator and, or, the BSW. 10. Water salinity, if any water. Measured using salinity meter, and it is often done by Riggs mud engineer. 11. Pressure, temperature, and flow rates plots, versus time. Acquired using surface well testing data acquisition system. 12. Oil pour point, and viscosity. Rarely asked during a surface well testing. 13. Non-pressurized oil sample. Taken from oil outlet separator, or tank. Usually 4 liters or 200 liters metallic cans. 14. Non-pressurized water sample. Taken from the bottom separator, or water sight glass. Usually 4 liters or 200 liters metallic cans. Note: these are bulk, large quantity, samples. 15. Pressurized oil surface PVT sample. Collected from the bottom oil sight glass of the separator, using pressurized oil sample bottle. 16. Pressurized gas surface PVT sample. Collected from the vertical section of the separator gas outlet, using pressurized gas sample bottle, 20 liters. Note: oil and gas samples should be taken at the same time, under separator conditions. 17. Bottom hole sample. Run in hole a bottom hole reservoir sampler in front of the perforations, to catch a representative fluid from the reservoir. As soon as fluid, reached to surface, rough gas composition, is taken at the choke manifold sampling point, using sniffer, or Draeger pump, and reactive tube of CO2 and H2S. From the choke manifold, sampling point, 2 equal fluid samples are collected in 2 straight glass tubes, in order to be centrifuged for BSW measurement. After centrifuging the tubes, using manual or electrical centrifuge machine, the oil, water, and sediment will segregate by gravity, and a BSW reading will be possible. For example, the BSW reading on this picture is BSW equal to 40% with 25% water and 15% sediment. The wellhead pressure in PSIG may be measured using the deadweight tester. The oil gravity is measured using the hydrometer with thermometer. The API gravity is obtained by dividing 141.5 by the specific gravity at 60 degree Fahrenheit. The well test results. Long-term results are given to the reservoir engineer after interpretation using well test data. Bottom hole pressure, generally, from final buildup. Flow rate at surface versus time, and oil and gas specific gravity. Geology data. Porosity and viscosity. And drilling data. Pay zone and wellbore radius. The long-term results for the reservoir engineer includes 1. Permeability, K. For example, K equals 10 millidarcy, this is a tight formation. K equals 500 millidarcy, this is a high permeability formation. 2. Skin factor, S. Which is the vicinity of well bore around perforations due to mud, mudcake, and perforations system. For example, S equals 10, this means a damaged formation. S equals 2, or minus 1, this means a good formation after acid job. 3. Obtain initial or average reservoir pressure, PI. 4. Calculate the radius of investigation, RW, or drainage area. 5. Determine presence of reservoir discontinuities or anomalies such as boundaries, fractures, etc. 6. Check reservoir limits and estimate reservoir size. 7. Evaluate well performance, productivity versus time, from any tendencies observed during the test. Chapter 11. Productivity. Productivity Index. The productivity index, PI, is equal to the oil or gas flow rate, Q, in barrels per day, or standard cubic feet per day, divided by the difference between the reservoir initial pressure, PI, and the reservoir flowing pressure, PWF, in PSI. The unit of the productivity index is then barrels per day per psi in the case of an oil well, or standard cubic feet per day per psi in the case of a gas well. Absolute open flow. The maximum flow potential, or absolute open flow, is the rate at which a well would produce at zero sand phase, bottom hole, back pressure. The absolute open flow, AOF, cannot be measured, and probably not achieved in real life, during well testing. Oil well, AOF. In the case of an oil well, the maximum flow potential, or absolute open flow, AOF, is obtained by plotting the bottom hole flowing pressure versus the production rate on a linear plot. This plot is called the inflow performance relation, or IPR plot. Oil well, absolute open flow, AOF. The inflow performance relation, or IPR plot, is obtained by plotting the bottom hole flowing pressure, PWF, in PSI, versus the gross production rate, Q, in barrel oil per day. This point here is the bottom hole shut-in pressure. This is the true IPR curve. The slope of the true IPR curve will give us the maximum flow potential, or absolute open flow, AOF. The slope line of the true IPR curve represents the ideal IPR curve. The slope value of the IPR curve is the productivity index PI. Gas well, AOF. In the case of a gas well, the maximum flow potential, or absolute open flow, AOF, is obtained by plotting the pressure squared difference versus the production rate on a log-log plot. Deliverability tests are done to determine flow capacity and to predict flow rate decline over the life of a well. Gas wells with AOF greater than 50 million standard cubic feet per day are classified as high productivity wells. Gas wells with AOF less than 50 million standard cubic feet per day are classified as low or average productivity wells. For a high productivity gas well, we normally perform back pressure test. A cleanup, from few hours up to 24 hours. An initial shut-in period, twice the duration of the cleanup period. A main flow period at 4 different rates, from 4 to 8 hours on each choke, with stabilization. A final shut-in period, from 12 to 24 hours. Note: there is stabilization when delta P is less than 0.1% the wellhead pressure every 30 minutes. For a low productivity gas well, we normally perform isochronal pressure test. A cleanup, from few hours up to 24 hours. An initial shut-in period, twice the duration of the cleanup period. A main flow period at 4 different rates, from 4 to 8 hours duration on each choke, with stabilized shut-in periods 6 to 12 hours between flow. The final, 4th flow period, extends until stabilization. A final shut-in period, from 34 to 72 hours. For a low productivity gas well, we also perform modified isochronal pressure test. A cleanup, from few hours up to 24 hours. An initial shut-in period, twice the duration of the cleanup period. A main flow period at 4 different rates of equal durations, from 4 to 8 hours, with shut-in equal periods between flow, no matter if stable pressure has been reached or not. The final, 4th flow period, extends until stabilization. A final shut-in period, from 34 to 72 hours. The modified isochronal test is shorter than the isochronal test because there is no need to wait for stabilization apart from the last flow. It saves time and money, but the results are less accurate. Recent software products available for well test data interpretation offer greater flexibility of test program needs. The traditional approach, such as back pressure and isochronal test, can be modified to reduce the numbers of flow and hence the overall timing of the test. Thank you for your attention. This is the end of today's presentation. Please hit like and subscribe to our channel in order to help us produce more content like this one. See you in a next video presentation.